Now we have Antoine Falaize, and we will jump to a completely different subject, but there is always mathematics behind it. Please.
Okay, so thank you all, and so hello for everyone I didn't see in the morning, and thank you for the organizer because the voice. Okay, thank you. Thank you to the organizer because it's a great pleasure to be here in Arpino, to hear all these really different but still interesting talk we had from the beginning, and to give me the opportunity to present work that is not, there is some parts that are new, but it's a long-range work with Thomas Elie and David Rose from IRCAM laboratory. So I am Antoine Falaize. I'm currently a research engineer in scientific computing at the La Rochelle University in a laboratory about engineering science for environment, so totally different subjects than sound and music. But I continue to work with both colleagues, Thomas and David, on this question. So I will talk about the Port-Hamiltonian Formalism, so just a paradigm, a view of modeling for the passive-oriented modeling and simulation of multi-physical systems. And specifically about audio and acoustic systems in this sound and theory of modeling. I think it's just in between both. So Thomas Elie was my PhD supervisor, and we started to work on this subject and started to build a numerical tool that we are still improving with a collaboration still with Thomas Elie and now with David Rose, who is in the same laboratory at IRCAM. So I will speak about sound synthesis mostly, and so first thing is it possible to define this subject? So there is a lot of possible definition, but I will take this one. So the idea is to develop a set of technological methods for the generation of audio signals. So it's artificial generation. I mean, I'm speaking now, so I'm making somehow an audio acoustic signal, but it's not about that. Here we are speaking about electrical signal mostly, and now numerical, but historically it was electrical, and it started a long time ago. And first maybe attempt to do such thing was made by Tadeusz Kail at the end of the 19th century, so with the telharmonium. And this was quite a big beast, in fact, because the idea of Tadeusz Kail was to propose to customers to be able to listen music through the phone. So you just take your phone and you can ask to connect to a specific wire, and you add some music, but at this time you didn't add any amplifiers. So you had to make a really big electromechanical system to be able to transport the sound with a sufficiently high volume to the customers. And so there was a keyboard with this instrument. So the idea here was you had some rotating wheels with some teeth on those wheels, and so you just control the rotation, which was the frequency. And so you had a keyboard to control the instrument, and the player was playing all night long and all day long. But you could not stay in the same room because it made a lot of noise, and the instrument took an entire building. In fact, so it was like not really portative instrument, but it was the first attempt. And then things continue with things like the theremin from the Léon Theremin, Russian engineers. So the idea here is totally different. And for first, it's really smaller, and here it works with inductive capacity. In fact, so you have two control. With the right hand, you control the pitch of the notes, and with the left hand, you control the volume. And with these two controls, so you can play some really continuous spectrum of notes and continuous volume, and so it was not like the clavecin with specified volumes. But the difficulty here is that each movement, even of the player, was affecting the sound. So you had to stay really quiet and just moving really slowly your hand. So you have some videos, but we don't have the speaker here. So I will, in the next part, show you, make you hear some sounds from this instrument. So continuing in the short overview of analog sound synthesis. So we had in the 20th century, so Martenot, so still based on the magnetic phenomena. You had the onde Martenot. So this instrument has some specific characteristic because you had two ways to play it. So either you play with a continuum pitch, or you play it with a keyboard, which is like a piano, so you could really play like traditional music, but with a really specific sound. And this instrument is part, so you have the keyboard and the controller here. So again, I will show you a video and make you hear this really specific sound. And one thing was this projector, in fact, which was like a palm, and you had a lot of wires that just made some interesting vibration that coupled with the sound of the instrument. And so this is why this instrument is really specific and really recognizable. So just continuing, so you have the Hammond organ in the made by Lawrence Harriman. So this could be just think as a short version of the telharmonium, benefiting from the improvement of audio amplifiers, and specifically a tube amplifier at this time. And this instrument was really used during the 20th century, mainly in the 60s, and a lot of rock bands used, the blues and rock bands used this instrument. And so now changing the way, so it's okay. So now we are speaking about creating sounds, but another way at this time, because we had the technology at this time, was to just make what we are calling now sampling music. So the idea is just you record a sound and you just play it after. And the Mellotron is one of the instruments that follows this idea. So in fact, you had like a weight here that is connected with wheels to a band here, magnetic band, which is like a tape, in fact, like the tape you had previously. And so when you actually, when you push on the key here, you just freeze the weight that just go down by the gravity, and so it takes the band with it, and this is just played. When you release the key, so you have a mechanism that just takes the tap back in the slot. And so this is mainly known for being the intro of Lullaby by the Beatles, so I will let you hear that. So the sound was really specific because you had to record each note of an instrument, like a clarinet, something like that, and then you can play the clarinet with your keyboard. So at this time it was okay, like a strong thing. And so lately we just arrived with what we have now in mind when we think about synthesizers, analog synthesizers. So the first really iconic instrument was the Moog, where you have some electronic oscillators that you can couple, and with some control which are relating with how the keyboard influences the oscillators, and you have some effect like you can mix them and do a lot of things. And so this instrument was really used in the 80s, in fact, and it just come back in the game because these instruments are now really priceless, because the sound was really characteristic, and you can it's hard to reproduce them currently. And in the same idea, you had the Oberheim Obi-Wan. So for Star Wars fans, Obi-Wan Kenobi comes from the name of this instrument, because George Lucas was really interested in the sound of this instrument. Okay, so I could speak a lot of about analog sound synthesis, but in fact, all these things are just a signal approach. So what you try to do here is you try to produce a signal that will have some specific frequencies, some specific evolutions. And traditionally you have two approaches. The first thing is what we call additive sound synthesis. So the idea you take just sine waves, and you add them, and you try to reproduce the target sound. But this is difficult. You could need a lot of sines to make a dedicated sound. So it works really well if you want to reproduce the argument, because this is exactly how it works. You have wheels that produce pure sine waves. But to reach complicated and rich timbre, it's really, really difficult. So another approach was, to make this with frequency modulation. I don't know why it is split on the right. So the idea of frequency modulation is, instead of adding the waves, the pure sine waves, so you take two waves and you somehow made the product. And based on basic trigonometric rules, so you end up with specific frequencies arising from this. But the difficulty here is like you don't know how to control them. So you have a specific sound, you want to reach that sound, and it's just trial and error, and you don't know how to tune the parameters of the sine waves to reach a target sound. So this was the functioning of this instrument that was very famous and still famous for the bizarre sounds it can produce, but it's difficult to have a realistic sound. So what we took an approach, so I don't know why why it is splitted, because, sorry. I'll just go back. It's better. So the approach we are taking here is sound synthesis by physical modeling, and here the definition is really clear. So the idea is to generate agno signals again, but by the numerical solving of an idealized, usually, maybe not too idealized, but usually idealized mathematical modeling of a given physical system. So the idea is just you look at a system like a brass instrument or string instrument, and you write down the equation for this system, and you try to solve them numerically, and you hear directly the sound of the system. So here are a few examples of such acoustic or audio systems that I will cover during this talk. And so you have like traditional orchestra instruments. Here, loudspeaker that is really needed to hear the audio signal you are producing. Here you have a keyboard. And when we speak about physical audio system, in fact, you don't only think about instruments. You can also have systems that just transform existing sounds. So this is the case of this object. So it's what we call a pedal. So it's with your foot you control the sound, and you can change the sound this way. So I will try to cover the instrument, and yes, based on this idea of generate the agno signal. But the question is, why would we want to do such a thing? So, of course, there's a scientific appealing aspect, because this involves, for the modeling, mathematics, physics, and when you want to solve the equation, you have computer science that enters the game. But also from a musician or user point of view, so it could be interesting to have several instruments or systems in a single computer instead of transporting a lot of keyboards, that it was the case in the late in the end of the previous century. Yes, you could improve the sound you can use to compose things. This is what interested like the composers at IRCAM. When we exchange with them, they found of a lot of new sounds, and so we can experiment things. And another thing that is we had in mind is we can just build a numerical laboratory to make sound experiments. but that respect the physical principle. So the idea is, okay, imagine you would like to have a beam that vibrates like wood, that have the perceptive frequency of the wood, but with the magnetic properties of metals. Okay, maybe this material does not exist, but if it exists in the universe, okay, we can hear the sound of this instrument, of this material. And this is, in fact, okay, maybe not the most, the greatest interest, but for musicians, this is experimental musicians that experiment with sound. This is an interest. So the approach we will take to make this aim, so sound synthesis by physical modeling. So the thing we need, obviously. So this is based on numerical simulation of multi-physical systems. As I told you, you have electromechanical systems, acoustic systems, and everything. So this involves electronic mechanics, magnetics, of course, for transducers, and thermics, because this will change the sound, and the sound will evaluate. Like if you take the Moog, when you tune the Moog during a concert, at the beginning, so you have a fine-tuning of the frequencies, but because of the heating of the light and everything, so the instrument changes frequency over time. So this, if you want to be exhaustive, you have to model these behaviors. And speaking about behaviors, so obviously when you have self-oscillation of things like that in instruments, so you have a lot of non-linearities. When you look at the loudspeaker, so you have non-ideal behavior, so the sine wave that is entering loudspeaker does not, as in the electrical domain, does not goes out in the acoustical domain as it enters. So this is what we call non-ideal behaviors. And usually you have several subsystems when you think about an electronic circuit, so there is a high complexity. And standard method for solving that, so there is a lot of them, so you can look at the literature, but you, build a set of elementary physical models, and you connect them, and then you apply just ad hoc discretization method to hear the sound produced by this system. But the difficulty is, so first, the stability of a single model, of the model and of its simulation is not guaranteed, and this is worse when you connect several subsystems, so it's difficult to ensure the stability of the whole system. And we absolutely don't want that when we are producing sound, because this will make sounds that are growing in time, and so it's just impossible to use that, specifically at the frequency we are using in audio. So we are usually at 40,000 hertz, and so if you have any instabilities, it just go really wrong really quickly. But okay, so the point of view, the central point of view is the basic idea, in fact, and rather obvious. Physical systems are passive systems. So the idea is, okay, there is no free range. When we say a passive system, is that a physical system, we store internally given energy, and you cannot produce energy. Either in another way than if you provide, or so if you just take a minus sign here, you can provide energy to the system. Because if you don't act on the system can just dissipate the energy. So this is totally obvious, but this is really the central idea of the work we did. And the thing is, there is no free lunch. You cannot produce energy from nothing. You have to feed energy in the system, and so this is the basic idea. So taking this point of view, we can just structure physical models according to energy flows. So this is the first step. Then when you have one subsystem, you want to build a full system by interconnecting them, we want to ensure a structure preserving interconnection of this model so that the energy flows are fulfilled. And then you, again, use a structure-preserving discretization method to ensure that at the discrete level you have a notion of discrete passivity. And the result is, we ensure the stability of a single model, and you ensure the stability of the whole system by ensuring the proper interconnection. So here I'm speaking about sound and modeling of audio system, but generally for what we call computer-aided engineering software, so traditional software you use to make engineering problem, to treat an engineering problem. This paradigm is really a good thing, and this is my job to develop codes and informatic numerical simulation, and to have this point of view that is unifying systems and methods is really a good thing. So the cornerstone of our work is this formalism, the Port-Hamiltonian systems formalism, so which is just a class of system that had been introduced in the 90s. And so the two main creators are Arjen van der Schaft and Bernard Maschke. So this is not the first reference, but this is the most precise, earliest reference. And so the idea of Port-Hamiltonian system is to combine three paradigms. So first we have the port-based modeling, the theoretical mechanics, so differential geometry, and the theory of system and control theory. And so what you end with is a state space representation, which is structured according to energy flow. This is what we are interested in. And this guarantees the passivity of the models. And this is why we are focusing on this formalism. So just going through all the paradigms, just to give a short word. So the first paradigm was port-based modeling. Yes, this is a paradigm I will focus on, because we can discuss about the other if you want, but this is mainly the one that helps us to have a systematic approach, is this idea of port-based modeling, and then it's just technical difficulties. I mean, and the idea of port-based modeling for me is really central in this thing. So the idea of port-based modeling is, which has been quite late, and you can think at that like for electronic circuits, really a good representation of this paradigm. So the idea is it's introduced by Paintner. So it's like a unifying framework. So you just say, okay, I don't focus on specific physical domain. I just focus on the energy flow first, and just to arrive to this emphasis, they use the divide and conquer approach. That is, when you look to a physical system, okay, a physical system is just the interconnection of components. So two ideas, and these ingredients are quite obvious. So what is a component? This is an open dynamical system that can interact through ports. So this is port, the idea of port, and when we speak about that, it's just a couple of dual variables. So in mechanics, we'll think about force and velocity. Electronics, it's like current and voltage, or in thermics, you will use entropy variation and temperature, but okay, it's all work the same way. But what you just want to ensure is that when you define a port, the product of both dual variables is the power received by these components. So there is a notion of orientation you have to fulfill. And once you have defined your components with appropriate ports, you can now make them networks that relate the internal exchange in the system, that is between the component and with the surrounding of the system. Continuing with the second paradigm, which is based on theoretical mechanics, so that is differential geometry. So yes, here I think a lot of you know what it's about, and I just try to understand still this concept. But okay, at least I understood what we speak when we think about Hamiltonian system, and so the idea of this paradigm is just to provide strong and mathematically sounded structures for formulation specifically of conservative system. For dissipative system, I don't know a lot of results, but we know for conservative system, like we can write down a symplectic structure and arrive to Hamiltonian system. So here in the Port-Hamiltonian system theory, the underlying structure is directly given by the interconnection of the network, in fact. And so coupled with the port-based modeling, so we can describe that through what we call a Dirac structure. We have a word on that, but you can just think that as a generalization of the Kirchhoff laws in electronics. And so we are not totally, we don't totally agree with Vladimir when you speak about Dirac structure. We have different point of view, but for us this is sufficient to see Dirac structure like that. And the idea of this construction, I mean, Dirac structure with the notion of port-based modeling. So this allows to have general construction and to tackle open and dissipative components that are hardly described in the conservative or traditional mathematical structure in Hamiltonian formalism. And so an important property that we will use is that when you interconnect properly two Dirac structures, you have again a Dirac structure. So this allows to model complex systems based on just a small set of components. So we are still on this idea of bottom-up modeling. And the third thing is the control theory, because the two Arjan van der Schaft and Bernard Maschke were automaticians, so from control theory, and so they really wanted to emphasize the possibility to control the dynamical system via an input and output variables. So the control theory is a really wide subject, and I cannot explain that. But the idea is now, specifically now, is to preserve and exploit the properties of the physical system we have at hand, and like symmetries or conservation law, which are like quite synonyms based on Noether theorem, so the idea of passivity that we are speaking from the beginning is it can be really exploited to develop dedicated controllers or observers for this class of systems. And there is a specific theory which is called EDA-PBC, which is interconnection and damping assignment for passivity-based control. And really this is a strong tool to deal with a complex system and when you want to control. So just to fix the idea, so just take an introductory example. So the simplest instrument we can think of, which is a linear mechanical oscillator, so undamped and without control. So classically, we will define the configuration as the mass position. And here, in this case, this is directly the spring elongation, because we take the reference of the rest of the spring. So the velocity is just the derivative of the configuration. And we have two parameters here, the mass and the stiffness. And we just can define the momentum as the product of the mass times the velocity. So classically, when you took the analytical mechanics approach, so you will first define two energies, the kinetic energy, which is just m times the velocity squared divided by 2, and the potential energy associated with the spring. So here we have the elongation of the spring, which is the variable of interest to explain the potential here, is directly equal to the configuration. Okay, so this is it. You define the Lagrangian that depends on the configuration of the velocities as the difference between both energies. And you have the variational principle of least action principle. You obtain the equation of motions, that is the Euler-Lagrange equations. And through a Legendre transform with respect to the variable q dot, you can define the Hamiltonian. So with the Legendre transform of the Lagrangian, which is now just the sum of the energies, but explained on the momentum and the configuration. And so now the equation of motion rewrite as the variation of momentum over time is the minus the derivative of the Hamiltonian with respect to the configuration, and by construction you have the velocities that are given by the derivative of the Hamiltonian with respect to the momentum, and you end up with a dynamical system, a first order dynamical system, which can be written as the derivative on the product space. So simply the derivative of the momentum and the configuration. You have here skew symmetric matrix that can be associated with the inverse of the symplectic form, and here you have the gradient of the Hamiltonian. So this is the classical way, and okay. The one consequence of this construction is directly that this system is conservative. The sum of energy it does not vary over time. So this is a conservative system, we are sure, and this is encoded in the equations. So now, if we take the same system but with the Port-Hamiltonian system approach, so again we take the component and interconnection ID. So first, the inventory of the component, we have one mass. We will associate to this mass a state, so it's x here. Sorry, I don't have. So x will be directly the momentum. You have the energy stored. This is the kinetic energy expressed on this state. And you define the velocity part as directly the derivative of, I'm sorry, I have a macro that just jumped somewhere. I'm sorry, so I will just explain it. So you have the velocity that is directly the derivative of the Hamiltonian with respect to the momentum, and you have the force, which is just the inertial force, which is directly given as the time variation of the momentum. For the spring, you will have the state that will be just the elongation of the spring. You have the potential energy here, and you will think about the velocity part directly the time derivative of the elongation with respect to time, not the configuration, but directly the elongation. And you have a force part here that is the derivative of the Hamiltonian with respect to this state. So, okay, I'm sorry, I had a macro problem here. So the energy variable here will be just the two states, so xm and xk. So this is the complete state of our system. We define the Hamiltonian function, which here is the same as previously, but is important for the subsequent development to differentiate it. So this is still the sum of energies, and the equation of motion are directly given as the effort here, that is the inertial force, is given as the derivative of the Hamiltonian with respect to the state of the spring here. And by construction, you have the equality of the velocities. So you end up with this dynamical system, which is really quite similar to previously. So here there is no real interest. So you don't see a lot of difference between both approaches. But if we take more difficult system, I think not hugely difficult, but somewhat different. So here we have two mass and three springs. So here the configuration is just the position of both masses. The velocities are the same. You just have the mass matrix, a stiffness matrix, where you have the parameter of the system. The momentum are just the mass matrix times the velocities. And you have to insert this variable here. The elongation are not directly equal to the configuration, but rather you have to say compared with the length at rest, and you have to say to express it in function of the configuration. So you have like a connection matrix that will be multiplied by the configuration, and so you can write the elongation in a quite different way compared with the previous example. So, running exactly the same way with the analytical mechanical approach, so explaining the energies, the Lagrangian, expressing the Hamiltonian as a Legendre transform, you obtain the equations of motion in a really similar way. So you have the derivative of the momentum over time, which is minus the derivative of the Hamiltonian with respect to the configurations. And if we look at the Hamiltonian here, we see that the derivative of the Hamiltonian with respect to the configuration shows this matrix C, which is related with, which relates the elongation to the configuration. So it appears explicitly here inside the Hamiltonian. And by construction, we see all the velocities. So the dynamical system here is a canonical Hamiltonian system. You have a derivative of momentum and configuration. You have this canonical skew-symmetric matrices and the gradient of the Hamiltonian. So still, we have a symplectic form, and this is a conservative system. Okay, now if we do this the same way for the Port-Hamiltonian system approach. So here we have the two masses when we make the component inventory, and we have the three springs. So here the state will be of dimension 5 because you have the 3 elongation associated with the 3 springs and the 2 momentums. The storage functional is still the same as previously. You just sum the potential and kinetic energies associated with the masses and the springs. And the equation of motions here, we need, in fact, because we express the Hamiltonian with respect to the elongation and not on the configuration, so we have the inertial force here, which is the derivative of the momentum over time. We need to insert this C matrix that relates the configuration with the elongations. And so the dynamical system we end with, so it's a system with dimension 5. Okay, it's quite similar to previously, but the thing is, here we have explicitly the connections that appear in the structure matrix. And this is really the difference compared with previous results. So. No, here, no, it's a one-dimensional system here. Okay, but this is generalized to any dimensions. The idea is just to fix how we can, what is really different in the approach compared with what we know as a Hamiltonian system with Port-Hamiltonian system. The difference here is just we don't, in fact, in the classical analytical mechanical approach, the connections are inside the Lagrangian. Here, no, we have the connections that are inside the operators that relate the gradient of the Hamiltonian with the derivative of the states of the system. So it's really a state space representation more than like a traditional with tangent and cotangent model and everything. So it's quite different. So the thing is, because of skew symmetry here, we still have the time derivative of energy 0, but we have a degenerate 2 form. So obviously this is not symplectic. Could it be Poisson? Maybe. But just remember that, okay, we are not speaking about only conservative system. We want to see dissipated power, and we want to control the system also. So we need to take into consideration this part. And the way Port-Hamiltonian system use that is, as I saw in the introduction, so you have the time variation of energy, the dissipated power, and the power, the sink power or source power, which are related through this Dirac structure that ensures the proper interconnection of the subcomponents. This is the idea, main idea. So in fact, I can say, okay, here is the central idea. Now I can just run through examples. And I see the time, so I don't know if we recover time now or after. Or
I don't know if it depends on if the... No, it's perfect actually, sorry. I was wondering if the coffee break was ready.
So I can't...
Whatever you want.
Okay, okay. Okay, so now, okay, so this is the idea, and so now if we just want to sketch how we make things work, so again, we have a multi-physical system. We will divide its component, so in port-based modeling, the components are divided into storing component, dissipative component, and ports, and the network will be associated with the Dirac structure. So now we have Port-Hamiltonian system, a continuous time Port-Hamiltonian system, and thanks to a structure-preserving numerical method, we can arrive with a discrete form of the power balance, thus ensuring the stability of the simulations. So this is really the base idea. So the slides are quite dense, and I think I will just run now quickly to the examples, because I think a lot of you are interested with that. First of all, I will describe how, in practice, we deal with the networks. That can be just think as you take a physical system and just remove the component, just forget the component. That is a constitutive relation associated with specific behavior in the system, and you end with just the connection of the system. So one really formal definition of a Dirac structure that is not the same as you could find in the differential geometry literature, because in this you need to define some Dorfman brackets, and encore the application is like, okay, still don't understand the classical definition, but for us it is sufficient to consider an n-dimensional vector space A, so what we will call the flows, the space of flows, and its dual space, the space of effort, and we just construct the product space, which will be called the power space, with the classical duality product from a pair of elements in from two elements F and E, so a flux and an effort. You just end with okay, duality pairing, classical, and just defining a symmetric pairing, which is the only one you can define if you have two elements in the power space. So F1, E1, F2, E2. You just make the symmetric pairing F2, E1 plus F1, E2. And based on this symmetric pairing, you can have the definition of Dirac structure as a linear subspace inside the power space, which is its own orthogonal, based on its own orthogonal with respect to this symmetric pairing. This is the idea. So, okay, this is a formal definition. We want to use them to produce sound again. So, the idea you have two representations: image representation and kernel representation. But okay, this is okay, technical details. The idea is, the practical consequence is that for each element inside the Dirac structure, so in the subspace of the power space, you have that the duality of the flow and the effort are zero. And this is really the generalization of the Kirchhoff laws in electronics, and the thing that ensures the passivity of the system. Maybe I will just run quickly to a first example, and then have a break just to see. So for us, just to systematically and automatically derive the Dirac structure associated with a system, we are based on the notion of power graphs. So the idea, okay, this is a graph, we have nodes and edges that are just a couple of elements in the set of nodes, and you have a direction, so it is directed edges. So the effort will be what we call the variable across. That is, you would have to define some quantities on the nodes, and the effort will be the differences, so oriented differences of these two quantities. And the flow is what we call the variable through. And the power received by the edge, so we are focusing on the edges, is just the product of the two elements. So again, this is a port-based. And again, the bottom-up construction is like, okay, you want to connect two elements, okay, you just perform node identification. That is as simple as that. So classically, if you take an electrical graph, you will have the current across and the voltage, the current through and the voltage across each edges. So this is quite direct from a system to build a graph. For mechanical graphs, so you have two ways of thinking. So I prefer this way when you make the electromechanical analogy, when you associate to the potentials here the velocity. So because here you can say, okay, I have a reference velocity, which is my datum in my graph, which is a datum in the electrical graph, and okay, you just look at your system, you can say, okay, I have this velocities, and I just connect the element I have to them. Because usually you have a dual representation of a mechanical graph where you associate to the nodes some force potential which are to be defined, you don't know what they are. And when you see the system, to have to this graph for me is more difficult, but okay. When you look at the mechanical graph, so we have the same. We just have to define here some magnetomotive force on the nodes, and you can have difference of magnetomotive force across and the variation of magnetic flux through. Again, the product of these two quantities is a power. And for thermal graph, you define the temperature on the nodes, difference of temperature. So if you look at like a box heating through a membrane inside another box, so you have 3 temperatures here with the base 0 temperature. You have 2 temperatures, and you just look at your system and say, okay, the component here, air, is just exchanging between the both nodes, both temperatures, and we need 2, in fact, to ensure the second principle of thermodynamics. This is the idea. And okay, we can just switch from a domain, physical domain to another, so this is quite direct. And okay, I will just say a word on how we automatically derive the Dirac structure in our system, and then maybe we have a break to go through then short definition of component and musical applications. So the idea is now we have a set of, excuse me, I'm missing just one definition. So now we want to define the Kirchhoff law graph, or the Telegraph structure that is associated with what we call a Dirac structure. So based on the graph, we can define the incidence matrix. Okay, it's just a matrix. You have all the nodes, all the edges, and you just say if the edge is ingoing or outgoing a given node. So you end up with such a matrix. And you have to be careful about the datum node, because the description of the dynamic of a system should not depend on the reference you choose for the velocities, for the potential, etc. See, like the birds on the wire we saw yesterday, the reference is not important. It's the difference between elements that is important. I mean, the absolute value is not important. So we are focusing on the reduced incidence matrix. We just forget this datum node. And so now we can write the generalized Kirchhoff law. So based on this reduced incidence matrix here, we have for all quantity on the nodes that are defined on the node, the potentials. So you have the effort are given by the transpose of this reduced incidence matrix times the potentials, and you have the Kirchhoff current law, which is equivalent at times that states that the reduced incidence matrix times the flux is always 0. And so based on that, what we can do is just splitting component as effort or flow control. We have effort and flow on the first part here, and effort, again flow and effort for the other part here. And we see directly that in fact we end up with this skew symmetric matrix that can be defined based on just a graph analysis. So I mean, this is quite straightforward, but provided we have this realizability criterion. This is again some technical detail, but usually it's okay. If it's not okay, we have some techniques to merge edge, etc. But okay, we can so automatically, based on the graph, derive this Dirac structure. And again, this structure, because of skew symmetry, this is a Telegraph theorem. We ensure that the sum of all the power that are plugged into the Dirac structure is 0. And now we can go through the passivity of models and to sounds we will have next. So again, this is the automatication construction with the realizability criterion. And so now we'll speak about components dedicated to audio and sound things. So I will stop now. Just start with some video examples of the system I described previously, just to make you have a taste of the whole old sound we had in the old landscape sound we had at this time. So starting with the theremin, which is such a really specific instrument. So again, just focus on the posture of the musician. So this is theremin itself.
Это песенно-голосовой инструмент. В нем управление мелодией достигается посредством влияния на электромагнитное поле около инструмента.
So you have a piano behind, but here's the sound. So at this time, at the beginning of the 20th century, it was like really surprising to hear such sounds, and so this changes the way people think about sound. So going now to still a magnetic-based sound production. So speaking about the own Martenot instrument. So this is a famous improvisation that is that has been made by Thomas Bloch. And when you see the two way of playing the instrument, is a continuum. So you have a band and the keyboard, you can play both. And excuse me?
Just a finger.
Yes, you have a ring just to control the magnetic field. And so these are instruments that are less used, and this instrument is really, really known. This is the Hammond organ, which is really used in blues, and so the short version of the telharmonium. And so this cabinet is really special. You have a rotating speaker inside that participate to have this evoluting sound. And you can change the number of ways that are playing the sound, so changing the number of harmonics you have. So this is what he is doing. As I said, the mellotron here is the intro of Lullaby by the Beatles, and the sound you hear at the beginning is played with this instrument that you just release a tape that is just playing around. This sound is played by the mellotron instrument. So, and after okay, so it's some and now going to the what we are now in mind when we speak about synthesizers. So this is the M&MoCS instrument, and again a signal approach to sound synthesis. So you just play with sine waves and try to mix them, making distortion and everything. And so the filters that are used in this instrument are really typical, and so my PhD supervisor made, for example, software to reproduce this sound. So, excuse me?
Can you play against Martenot?
Yes. Okay, so we could expand on that later. So coming back to the theory of modeling, so we spoke about the system as being the interconnection of components. We saw the interconnection that is associated with a mathematical structure, which is a direct structure. And now we speak about the components, just how to ensure that we have the proper behavior, that storage of energy and dissipation and ports. So starting with storage components, so the idea is to just store an energy and exclusively storing energy. So the idea is quite simple. We have the stored energy as a function of time, which is expressed through a state variable. And so the energy is positive definite. And the power received by, again, the arrow here are really important. So each part receives a power. So the power received by storage component is just the time variation of the Hamiltonian. That is by a chain rule. You have the derivative of the Hamiltonian with respect to the state times the derivative of the state with respect to time. And so the power variable here, so again, we want that the received power is a product of two quantities, and seeing that, okay, we directly associate this product to this product. So now the question is, who is the effort and who is the flux? And so we have two kinds of storage component, depending on who is, again, the effort and who is the flux. And now if we have a lot of edges or components, so we have multidimensional states. The total energy is just the sum of all the energies, and we have this quantity, which is the total power received by the storage components. So some example just to fix ideas. So if we think about a mass, here the flow will be the velocity, and the effort will be the inertial force. So the state is the momentum, the Hamiltonian is the kinetic energy, and the flow is directly the velocity of the mass, that is the time derivative of the Hamiltonian with respect to the momentum, and the effort is the derivative of momentum with respect to time, which is the traditional quantity. And looking to like a capacitor in electronics, so here the state will be the charge. We have electrostatic energy expressed on the charge of the capacitor, and here we see that comparing with here, where the flow is the derivative of the Hamiltonian with respect to the state, here the flow is the derivative of the state, and we have the effort as the derivative of the Hamiltonian with respect to the state. So there is again these two kind of components. So now this is quite obvious. Now looking to the dissipative part of our systems. So the constitutive relation for component D will be expressed based on the dissipation function of a given variable, so dissipation function Z and the variable W. So the received, that is totally dissipated power, will be expressed, it is missing here, the total dissipated power is the product of the function, dissipation function applied to the dissipative variable times the dissipative variable. So again, we have a product of two quantities, and we have to choose which one is the effort, which one is the flux. And similarly for several dissipative components, so you have a dissipative variable, multidimensional function, and the total dissipated power is just the sum of everything. So. As examples, so again, if you take a dashpot, it's just a linear damping, so we will choose the variable as the velocity. The function will be just the resistance forces, so we have a coefficient here d times the velocity, which is the resistance force. So the flow here is directly the force, and the effort will be the velocity. So we have these two, and the power, dissipated power is the product of both, which is positive. And consider a resistor in electronic. You have the variable will be chosen as a current. The function will just be the resistance voltage, that is R, which is resistance times the current. So here the flow is the current, the effort is the voltage, voltage, no velocity here, which is R times the current, and again the power, the dissipated power is positive. And then going to the last part, which is the port. So the question is for each port we have, which is the quantity we are controlling and which is the quantity which is observed. And we will define the received power by the edge. That means the power that is leaving the direct structure as a product of both quantities. Okay, so this is the power that goes out of the systems. the powers that go inside the edge is the powers that go outside the system. And we have to choose again between which is the effort, which is the flux. And so as examples, if you take a voltage source in electronic, you will choose the input quantity as the voltage, the output will be the collected current. So flux and effort are obvious here. The product is again the power, so product of both, it's obvious. And if you think in mechanic, you impose a force. Here the input will be the force, the output will be the collocated velocity. So this could be difficult in practice because to measure the velocity collocated to a force that you apply can be quite difficult. But so here the flow will be the force and the effort will be the velocity. And the received power is still the product of both. So now, putting all together, we have a complex scheme. So we have our components that we have storage, dissipation, and the external port. For each, we have flux and effort variables. The network will just relate all the flow and all the efforts through a skew-symmetric matrix. And so because of the skew symmetry of this matrix, so this is the direct structure that ensures that the product of the dot product of the effort on the flux is 0. And in fact, if we just develop based on this definition, we have the gradient of the Hamiltonian times the derivative of the state. This is by definition the variation of energy. We have the dissipation function times okay, we have a transpose here. The dissipation function times the dissipative variable, which is dissipated power, and the power flowing out of the system. So this is what we think of a physical system. For us, it's just this. And each physical system we treat are defined this way. So the structure is something like that. Again, storage, dissipation port, and so all models we are treating are defined this way. Just a word on the reduction of linear dissipation, or maybe not linear, but at least dissipation that can be defined from the derivative of a Rayleigh function. So in this case, we can just define a matrix R here that describes the resistive interconnection, the linear resistive interconnection inside the structure matrix. And so this does not change a lot of things, just reduce a bit the system and give some insight, more insight in the interconnection structure of the system. Okay. So coming back to the conceptual sketch, and I'm almost done with the theory of modeling, and we go to sound. But so we explained the multiphysical system as this particular formalism, and now the question is how do we preserve this structure at the discrete level to have a discrete increment in energy that is governed by a power balance, discrete form of the power balance. So which numerical method to use? And so things are well known because this is a gradient system. So for a gradient system, there's a lot of work that has been done, and based on some old work in the late 80s. So again, the idea is to have at each sample, at each time step, this power balance that is fulfilled. So a choice is rather evident to define the increment in the energy as a difference between the energy at one step and the other, divided by the time step. So this is a one-step numerical scheme. So based on the definition of Hamiltonian, this will be something like that. So in the monovariate case, I mean, if the Hamiltonian associated with this, I mean, if for each state n, each state component n, we have a single scalar function hn. So just the total power here will be the sum, so it's a possibility or choose, will be the sum of the difference of each energies for each state divided by the increment in the state. And we have here a discrete time variation of the state. And this construction give us directly the solution. So we just replace the time derivative, or approximate the time derivative of the state by the increment of the state, discrete increment, and the gradient of the Hamiltonian will be approximated by a discrete gradient with the component n of the discrete gradient expressed as the difference between the two energies, so, from step k to step k plus 1 here, divided by the increment in the state. So, so we have a first order convergence of this kind of scheme. So we are at least at order 1 in time, and we can go further in order if we discuss. There is a work that has been done. So just now, our definition of a discrete Port-Hamiltonian system will be just making this approximation inside the structure, and the other quantities are just evaluated on a full time step. So on the time step k, we think as order 1 blockers. So the quantity here are just constant in the input observers specifically. And we just have our discrete gradient here and the discrete state increment. So we have a numerical passivity directly because we preserve this structure. But the difficulty here is first, this because the gradient of the Hamiltonian can be strongly nonlinear in real applications. So this need to be solved iteratively, typically with a Newton-Raphson algorithm, something like that. And so this can be explicited based on the quadratization, in fact, of the Hamiltonian. And but doing that, I mean, in a manner that is too not very clever, we can lost some order of accuracy, and based on Runge-Kutta-like method, we can recover second order accuracy if you want. So example of what we think. So okay, I just forgot to express the system here, but so we just look at the relative error on the power balance here for a conservative system. So we just look at the difference between the energies relative to the energy at the first time step over time. So we compare the discrete gradient method with the midpoint rule, the trapezoidal rule, which are quite different from nonlinear systems, and implicit and explicit Eulers. And we see that even when with big time step, we still have relative error which is close to machine epsilon, which is interesting for us. So we see that everything is now really formal and really abstract, and so we can automatize everything. And so everything has been implemented in a Python library, which is free available on GitHub. So the idea is we have a netlist, which represents the network. We have a dictionary of components inside the library. So the user just provides a description of the system, which is analyzed to produce the graph. I mean, just a network with labelization of components as flux or effort control or storage, dissipative, etc. So this is a symbolic graph. We can, based on graph analysis, derive a symbolic Port-Hamiltonian system, so in continuous time. We can apply directly the discrete gradient method to have the discrete time power balance, but still symbolically to perform optimization or simplification of the equation, of the algebraic equations. And then we can go to a simulation object where here everything is just okay. We have pointers that define the required memory and everything, and we can automatically produce based on that a C++ code that will be used for the simulation, along with LaTeX description of the system automatically. So in the current PPH dictionary include elements from multiphysical, so we have mechanics, electronics, magnetics, and thermics. With some interesting things, specifically, we can describe fractional derivatives, either in mechanics to describe viscoelastic component, with visco is the dissipative part, is the elastic is the storing part, and we have a component that is between both behaviors, and resistor or inductor, which is typically associated with eddy current. In loudspeaker, we needed this model, so we just add it, and okay, you just want to define the component, you can add it in the dictionary. It's just really straightforward. So a short example, taking a simple nonlinear model of speaker. So we have the electric part here with the coil around the magnet. You have the input tension in the coil wire, the resistance of the coil wire. The generator is directly associated with the Laplace force with Lorentz transduction. And you have here the mechanical domain, which includes the mass of the moving part, some damping that can be associated with the radiation of acoustic energy, and a restoring force here. And we just take a single nonlinearity here, which is the cubic force. So this is the netlist that the user should provide to the library. So we have everything, the source associated here, resistor, inductor here, and everything, with the parameters and with just the label of the nodes. So this is a typical netlist formalism. Importing the library, from the graph from the library, you just instantiate your graph object, and you can plot it. Then ask to automatically build the equations. So from the graph, you go to the core Port-Hamiltonian system formulation. So this core object has, like, for example, the state and the Hamiltonian. We can see them. So these are symbolic computation. We can derive them and do things. We can write the LaTeX description automatically. So I can show you if you want. And for the system simulation, we just define an input signal. So here it's just a sine wave. We build our simulation object that performs the discretization and the generation of the C++ code. So we have several languages. Here we just use C++. We can use Python or dedicated language for sound like Faust or Juice for people who know. And just run the simulation. And we have the result that is the variation of energy here in blue is exactly equal to the power dissipated minus the power that is going out of the system as defined inside. So this is really straightforward. Now going to more interesting example and specifically audio examples. So just taking the Dunlop Crybaby wah pedal. So what is subject? In fact, again, it's usually plugged on guitar. So you have the wires that go through the effect and then go to the amplifier, and it is actuated by the foot. So we just can find on internet the schematic of the circuit. And so, first with our approach, we just identify, which are the storing components. So we have a coil here, some capacitors. Which are the dissipative components? So obviously resistors. We have diode here that are nonlinear semiconductors, and quite complicated component like a transistor. Here, so to which we absolutely cannot associate a Rayleigh function. It's strongly implicit dissipation. We have to use the formalism to use that. And for the sources, so we have one port where we plug the guitar, one port which is output where we plug the amplifier, and we have a battery here, 9-volt battery that we have to plug. And so we can, based on this modelization, just change the battery and say, if my battery is just low, how will this system sound? So we can just perform some measurement on the system. So here we compare with a really well-established circuit simulator, which is LC Spice. And we see in the when the wah is just at the beginning. So these are the spectrum when you just run with a white noise inside. On the audio range, so from 20 Hz to 20,000 Hz. And we see the transfer function between the input and the output, so with a strong resonance here. And when you go in the wah position that is totally pushed down, you have this spectrum. And so we are quite pleased with this result. And just to, again, make you hear some sounds with the Crybaby. So first, a simple guitar riff, so just raw. And now pushing the sound inside the simulation, the discrete system we have, making just the wah pedal going up and down with a periodic, I think it's 1 second period. And this is... So for people who know, this is really a characteristic sound of the crybaby wah pedal, in fact. Okay, so now one thing is, okay, we just see, okay, we have a really small component, we build system based on this small component, but keep in mind that conservative interconnection of several Port-Hamiltonian system is again the Port-Hamiltonian system. So this is the composition of Dirac structures, and this is the strength of this formalism. So as an example, if you just take two beams and you want just to connect them with a spring, so maybe there is no interest to do that, but just for example, so first we take the classical Euler-Bernoulli modeling of a beam. So we have just a spatial variable. You have the deflect of the beams, vertical deflects, and then the Euler-Bernoulli modeling is a second order equation where you have here in fact the momentum. Here you have the dissipation terms, and here you have the bending force, the restoring force. With a distributed force here, so a point force distributed with gamma E compact support function, just to say where the force is applied on the beam. So we have this for each the east beam. We have two equations. So what we can do directly is just project this equation on the modal basis directly. And we end up with a finite dimensional system that can be written in the Port-Hamiltonian formalism, choosing the state as the deflect and the momentums. The energies are, okay, traditionally the sum of kinetic and potential energy. For the dissipation variable, we just choose the variation of the deflect velocity, in fact. With dissipation function, just a linear function with alpha, the damping coefficient. The input will be the force applied, and the output will be the velocity, the reconstructed velocity from the modal decomposition. So we end up with a Port-Hamiltonian system. In fact, if you just forget the dissipative and port part, you see you end up with a canonical Hamiltonian function, in fact, Hamiltonian system in this case. Now, if you want to connect both beams, first thing we have to do is to add a second port to connect with the control. So the idea is, so because if you come back here, so this beam should be connected to the spring and to the control that is applied on the beam. So we just add the control, so it's really straightforward in this formalism based on this structuration in control part, dissipative part, etc. The second beam is just the same as preceding. And for the stiffness, so okay, we have just here a really elementary Port-Hamiltonian system, which is just a spring with a single state, okay, it's not a gradient here, just the derivative of h with respect to x. And we have two ports here, so these are just the velocity of the endpoint of the spring. And so now just connecting the beam I with the spring k, so we just say the k input, the I input of k is given by the velocity of the beam at that point, and the input of the velocity will be minus the force which is the output of the spring. So this connection ensures that the power which is received by the component K is exactly the power that is lost by the beam I. So this is what we call the conservative interconnection. So no power is lost or created in the interconnection. And we end with, again, the Port-Hamiltonian system that is which a single input here, which is the control we applied in. And yes, all the components that are inherited from the modeling of each component. So now going to a more interesting application, because this was just a toy model to explain the connection. So we took the really famous instrument, which is the Thunder Rhodes instrument, and performed some, same thing, sound synthesis by physical modeling for the Thunder Rhodes. So just a short history of the instrument, because I just discovered that not too long ago. So, in fact, the instrument, it was invented during the World War II, so it was a small piano there was no so much notes you can play, so there was 2.5 octaves, so not so much. And in fact, at the beginning, the vibrating pen was just piece of aluminum taken from the wings of planes, war planes, because it was like during the war, so there was a lot of material like that. So it was a success, and specifically because this instrument could be taken on during the war to be played by the warriors, and so when they came back, they said, okay, it was quite known, but there was really a poor manufacturing quality, so it just it was not working too much, and finally he proposed a patent for an asymmetric tuning fork, which is the heart of the sound of the Rhone instrument. So based on this technique, he could build 72 key instruments. And Leo Fender, which is a guy of amplifier and guitar, which is very known, enjoyed it. So he proposed a collaboration, and the first Fender Rhodes appeared in the 90s. So now there is a lot of development, and now we will know the Rhodes as the Rhodes Mark II. Just to show you again, just to fix idea, how does the instrument sound? Okay, so this is really a characteristic sound, and usually we can hear them. So I just stay on the lowest part because this is where we really hear the sound of the instrument. So this is the inside of the instrument. So you have the keyboard, and here you have the tuning fork that has been patented by Mr. Rhodes. So just these are the mechanical resonators, so which are specific shapes, and that. Okay, this is how it works, and in fact, how it works, you have here some small magnets which are surrounded by coil, and in front of them you have the vibrating tiles that just vibrate in the magnetic field, and by electromagnetic transduction. In fact, we can explain that later, but you have the sound that is produced. So a detailed view of the instrument. So you have here a key, so you just push here, it will make the hammer here move, that will hit the tin here. So the tin is coupled to the resonator that will store most of the energy, and it will feed it back to the tin that will vibrate for a long time, so with a small tuning spring on the tin. And this is in front of the pickup here. So in fact, we just model these parts, and as I said at the beginning, so modeling this geometry is quite difficult. So in fact, this is what we model. So a simple cantilever beam. We have a hammer here that is a moving mass with a soft covering felt here, and the electromagnetic pickup here. So the first thing is the hammer. How do we model it? So it's just a moving mass again with here the constitutive the property of this felt material is just modeled with an elastic nonlinear elastic spring and a nonlinear damping. So these are storing, and this is a dissipative component. And the port here is just the contact condition with the moving part above. So it's a one-sided nonlinearity that just go inside the direct structure. So this is the classical dynamic of the hammer. So here you have the position, velocity, and acceleration. So at the beginning we just impose a constant force between 1 and 2 milliseconds. So this increases the velocity, and then we just let him go this way, his way. And when it hits when the position reached 0 here, so the hammer hit the beam, and so there is a compression, so we have a change of sign in the acceleration, and so the velocity start decreasing. And after a time, so there's just a rebound of the hammer. Okay, so this is really classical. But we can look precisely based on the formalism on the energies. So we have the energy of the beam, the dissipated energy in total in the hammer and in the beam, and we have the energy stored in the hammer, and this is the sum of all these energies. So we'll see, okay, we have again a power balance that is fulfilled. All the energy that is lost by the hammer is either gained by the beam or dissipated. And then when we let, after impact, the system, the beam vibrate, so all the energy in the beam is dissipated, and we have a power balance that is fulfilled. So now, okay, this is just the mechanical part. I'm now turning to the electromagnetic transducer and how we model that. So the idea is, again, we have a magnet here that will impose magnetization of the area here, and this is surrounded by a coil. So the coil is sensitive only on the variation of magnetic field. So for a constant magnetization, it won't see anything. But if you push a ferromagnetic sphere inside the magnetic field, so you will change the magnetic field. So if you don't move the sphere, it will just be constant. But if you start to move that, so the magnetic fluid inside the coil will change over time, and this will produce a tension in the here, the voltage here. So in fact, so just making raw modeling of this phenomena, we end up with such a graph. So here it's just an electrical part, it's just a filter, in fact. But the thing is, here we have the magnetization imposed by the magnetomotive force imposed by the magnet, and this will be modulated based on the position and on the velocity of the vibrating sphere. So here we have just the geometrical part that is here, and times the velocity of the beam the sphere, ferromagnetic sphere. And here you see you have two parameters that will be important for later. You have the vertical distance and the horizontal distance between. So this is the vertical distance, so between the sphere at rest and the axe of the magnet, and you have the horizontal distance between both. So now we can just look, just push, making the sphere vibrate. So we have here the variation of energy. So inside the electronic part, we have the dissipated power. We have the power that we are supplying by moving this part. And again, we are close to machine epsilon when we look at the power balance. So okay, we are happy with that. But now the question is, does this really work? So we have to compare this with a real instrument. So we have here the spectrum measured on a real instrument. So we just play several notes with increasing force on the key. So we have an enrichment of the spectrum, and we maybe do not see exactly the same thing here, but okay, perceptively this is I will make you hear the sound, but we can have a closed loop. So I will compare the waveform when we play the force 1, 4, and 7, and we will look at the beginning, at the impact, and at the tail of the sound each time. So when we look at force 1, we have the reference, that is the measurement and the simulation we have. So we see we lost in amplitude, and okay, it's quite similar, but maybe too much. But the question is, does the waveform evolve the same way in the real instrument and in the simulation? So we just increase the force. So we have modification of the waveform, which is associated with this enrichment of the spectrum. And again, at the beginning and at the end, we see we have really, really close behavior and hitting again more strongly the key. So we have still a big enrichment, and again, both are closed. So I will just make you hear the sound. So just remember the sound of the real instrument. Okay, we just stay with this one. And so we have several notes, and here these are the tests we are just hitting stronger and stronger the key. And you have the enrichment in the sound, and this is really the characteristic sound of the Fender Rhodes is this distortion, soft distortion you have in the waveform, so compared with a pure sine wave. So the thing which is really interesting in this physical modeling approach to sound synthesis is that we can approach really the behavior of the physical system. And if you take, excuse me, the user manual, in fact, they explain you how to tune the pickup position. And you say, okay, if you just make your pickup too far from your beam, from your tin here, too far you have a low volume, too close, we don't know what this means, but they say, okay, ideally you should be in between. So there is no measurement of distance anywhere. So, okay, we just try to control here the distance. So between so this is the horizontal distance we are controlling here. So if we are 1.5 millimeters, so we have a waveform that is that corresponds to what we are expecting. If we are too far, we see we lost the volume. And if we are too close, we have a waveform that has totally nothing to do with the expected waveform. So, okay, we are happy with that. And there is another thing, it is, okay, they explain you how to tune the vertical position. So, if you are exactly in front, so you will have a symmetry in the movement of the tin relatively to the pickup. So you have a pure overtone. If you are too low, too low compared with the axis of the tin, then you will have a pure fundamental sound because you just see a go and back of the tin on a periodic basis. And if you are just, again, ideal, what is this distance is not explained, but there is an ideal position where you recover the waveform. And this is exactly what we see. So we have zero decay in vertical distance. So here we have a pure overtone, so we just double the frequency. If we are too far away, we have something like this close to a sine wave. And if we are at 0.5 millimeter, here we recover the sound. So this is the idea of really approaching the physical system this way. Okay, so I don't know how time I have, Thierry or... Excuse me?
I think you have 10 minutes.
10 minutes, okay, so, okay, that's perfect. Just to finish, last application, I will just speak about the violin. So it's a well-known instrument, so that is played with the bow, that will have friction on the strings here. And we are just focusing on this part and specifically just on the interaction between the bow and the string, because then this is just impedance condition we can impose here and here to record like a filtering of the sound produced by a string. So basically, how does it work? So it is well known. This is what we call the M&MoCS motion. So you have an alternance of stick and slip phases, where the stick phase, you have the string that follows the motion of the bow here. And then with the back of the waveform, then you have the slip phase. Okay, so this could be like an idealized motion. So does this work this way? So there are some measurement, precise measurement we can find, and we see we have the slip, slip, slip. Okay, the ball is just going at a constant speed, and we exactly see this movement. So the M&MoCS motion is characterized by the sawtooth waveform that we would like to recover by physical modeling. So one thing is the string model, so I won't have the time to discuss that. We can do, okay, like take the partial differential equation, make a model decomposition directly, and obtain a finite dimensional system that we rewrite in the Port-Hamiltonian system formalism. But in this work, with David Rose, we choose to directly model the partial differential equation as what is known as the Stokes-Dirac structure. So it's like an infinite dimensional version of Port-Hamiltonian system, and thanks to a structure preserving spatial semi-discretization, we end up with an ordinary differential equation in the Port-Hamiltonian system formalism. But it's, I mean, it's a more coherent way to obtain the equation for the system from us. And from a theoretical point of view, there is a lot of things to discuss, but won't have the time here. And just to spend some time on the friction model, because friction are really a non-linear behavior, and so can we model that in the Port-Hamiltonian system formally? Okay, obviously the answer is yes. So we have here the bow, and we have two ports. So we have a port here, which is the interaction with the musician, and we have a port here, which is the interaction with the string here. And again, we can look at the power emitted through the ports of the bow, of the friction object. And again, we have a conservative interconnection, so thanks to the Port-Hamiltonian formalism approach. So for the friction model, we choose what's called the single-state elastoplastic friction model, known as the Dupont friction model. So like each friction model, we are just interested in the relative velocity between the bow and the string. So this relative velocity is usually decomposed as two parts. We have an elastic part, an elastic velocity, and a plastic velocity. So in fact, to define the elastic velocity, we just associate a state, which is in fact a potential energy, which can be seen as a state of the bristle that are between the bow and that are at the surface of the bow and are in contact with the string. So this is a reversible behavior, so it is associated with an internal storage of energy, and we have plastic behavior, which is associated with a dissipative component. Okay. So based on that, we look at the Dupont friction of model. So it is given by an implicit relation, which look like that. And the question, is this model passive? So looking at that directly, so it's okay. These are just technical details of the function that appear here, but we have the force of the interaction on the string that is given by this relation, where the time variation of the state here of the friction is given by this relation. So okay, it's quite complicated. Additionally, you have an adhesion map, which is okay, just won't spend too much time on that, but we have an expression here, so it's just a positive function that just describe that just avoid the non-physical creeping of the friction object. But so question, how do we formulate this model, this friction model, as a Port-Hamiltonian system? So the first question is, how do we identify the storage component? So it is directly associated with the elastic part. And then what are the dissipation variables? So we choose one dissipation variable to be directly the relative velocity. So in fact, this is the sum of the plastic velocity and the elastic velocity. And we will choose an elastic, a plastic force here, which should compensate exactly the elastic force, restoring force of the elastic part. And with choosing just this dissipative quantity, we end up with such modeling. So this is the output port, which can be expressed based on the conservative part and there's a plastic part. And now the time variation of the elastic part is directly related to the dissipation variable here. So the question is, how do we write a dissipation function for that? So we just introduce here coefficient of dissipation that will be modulated by the elastic state and by the relative velocity. And this, like damping coefficient, will just be multiplied by our dissipation variable as we saw previously. So this is really a damping coefficient, the positive damping coefficient. And so then, for us, the Dupont friction model can be written as this model. So we have the two velocities, the difference of which will provide the relative velocity. So if we take here, this is the relative velocity, we just have the difference between both velocities at the end. We have the elastic storing of energy. We have the two components of the dissipation function. And so the whole dissipation function Z here, that depends just on the dissipation variable and which is modulated or parameterized by the elastic state, can be just expressed as a matrix, a positive definite matrix, times the dissipation value here. So when we look at that, it is totally clear that, okay, the Dupont friction model is passive, and we can have, it is a generic model, we can just changing parameters, changing the structure of this matrix, we can change to switch from different friction models. So what do we have as a result? So again, we have the deflect of the string, the velocity, time derivative of the deflect and the acceleration at the contact between the bow and the string. So okay, we don't see a lot of things here, but if we have a closed look at the end of this waveform, we recover exactly the Helmholtz motion, which we would expect. And so we can further examine the relation between the relative velocity and the total force exerted by the friction on the string. And so we see this closed loop, so quite closed loop, which is related with the plastic part, which is just modulating the elastic part. So it would be exactly reversible if we just look not the relative velocity here, but the elastic, elastic component and the elastic force. But here we are plotting that with respect to the relative velocity. So we have this curve with both components, and so we can make further analysis on that. And again, so the running the concept from the beginning is the power balance, and we see that again we fulfill a power balance by summing the time variation of energy, the dissipated power, which is always positive, and the source power. So just to end, we will share the slide, and if you are interested in either the general Port-Hamiltonian system theory or infinite dimensional Port-Hamiltonian system, spatial discretization, I did not discuss too much, so you can look at these references. For me, it was really helpful. And so I thank you for your attention, and okay, if you have some questions.
Questions, comments?
I have a question about the numerical scheme you use, because all this development is so old, because you can simulate by preserving the energy. Is your numerical scheme encompassing, or is it compatible with both explicit or implicit approximation of the derivative? Can I choose my way to approximate the derivative?
So No, in fact, you have to specifically define the time variation of energy as the difference between of energy in the increments. So you don't have, I mean, the implicit part comes from the fact that to know the energy at the next time, you should know the state, and to know the state, you have the gradient of energy that appears. So everything is just totally mixed up. We can, the way, okay, I don't have the slide to explain that, but the way we can, as we did in this work here, when we explicit things, in fact, is just we are putting if the Hamiltonian is quadratic, so you have here a linear function, and you can just take some part on the left and some part on the right, and so okay, you can do things for quadratic Hamiltonian. If it's not quadratic, you can make like a linearization of the gradient by putting some information in the interconnection matrix that can that now depend on the state. But it's you don't have choices. In fact, you have to define the time variation of energy as you define the time variation of the state to make things compatible. In fact, here you have to be dependent on this state increment, and if you define the state increment this way, then the gradient of energy over this time step is defined this way. You cannot. We did not achieve to define it another way, and the way we can make it explicit is just because we put some information in the matrix here, and we say this matrix is constant on the time step. So this is not true. This is why we lose an order, and this is why we need some machinery to recover one order, small order accurate method. This is the idea. But there is no freedom, in fact, and not so much freedom.
When I look at your talk, my wife always tells me I'm talking too loud. Then Port-Hamiltonian systems are basically a good way of bookkeeping. When you have lots of little individual Hamiltonian systems, they're connected to each other, they're talking to each other, and then this formalism sort of takes care of describing that without going crazy. I think it's a good language. Now, when I think also of some earlier talks, say we have complicated Hamiltonian system. Do you have a systematic way of breaking it down into little pieces, which little elements, which then sort of systematically could connect the big thing?
So if I just understand the question, so you have an ordinary differential equation. Question, is there a Port-Hamiltonian system formulation?
Writing it like
So the answer is it depends. So first, we are modeling a passive system. So if you have an ordinary differential equation that is associated with a system in which you will have a supply that is not properly identified, or something like that just describe a non-passive motion. So obviously we won't achieve, or we will need to define some negative dissipation or something like that. So what we totally don't want. But generally speaking, no. It's a trial and error. You try to identify exactly as we did for the friction model. We just tried, okay, say if we define this quantity or this quantity as the dissipative variable, can I end up with the structure clearly identified, the interconnection structure clearly identified. We hope to do an automatic derivation, in fact, based on the modeling of equations as a graph. And then, by analyzing this graph, to produce another graph that could be interpreted as a Port-Hamiltonian system. But it's not straightforward, and this is an ongoing work. For simple system, it's really easy, but if you start to having some nonlinearity or some coupled components, and specifically in the friction in the model of friction here, you see we have the dissipation function that is modulated by the state here. So it is not clear how when you look at the equation, how to obtain this structure and to accept to have this dependency of the dissipation function on the state is not straightforward. So first you will expect to have a clear separation between dissipative and storage component. But here this is not the case. You cannot split them. So generally speaking, the answer is no.
From a user perspective, are there some bindings to make it easy to control the models, or with, say, music controller, like in MaxMSP or something?
Exactly. In fact, not with MaxMSP, but one thing is, I will try to reach here. Okay. Here, one of the outputs is a C++ code. But you can have other targets that could be like Faust, which is a dedicated language for VST plugin, or you can produce the C++ code to be inside in a Juice project, which again will produce you a VST plugin. And then your VST plugin, you can use it in musical software and control it with a traditional MIDI controller or something like that. But we don't manage this part. There is some ongoing work to automatically generate the synthesizer, like the VST plugin for a synthesizer. But then it is the responsibility of the hosting software to control the parameters. But what we do is the parameters are in fact are appearing in the C++ code. I could show you the C++ code if you are interested, but the parameters here, if you say, okay, I wish to control like this symbol in the C++ code, this is possible.
Okay, so